Half plexiglass, half air. A parallel plate capacitor is made from two plates. A is equal to 12 centimeters on each side and D is equal to 4.5 millimeters apart. Half of the space between these plates contains only air, but the other half is filled with plexiglass of dielectric constant kappa equals 3.4. So you can see half is plexiglass, half is air. An 18 volts battery is connected across the plates. Part A, what is the capacitance of this combination? Hint, can you think of this capacitor as equivalent to two capacitors in parallel? Part B, how much energy is stored in the capacitor? Part C, if we remove the plexiglass but change nothing else, how much energy will be stored in the capacitor? Now you can see we have the same potential difference being applied between the plates of this capacitor, the air capacitor, and the plexiglass capacitor. Therefore, we can think of this as plexiglass capacitor parallel to the air capacitor connected to this battery with the common potential difference. Since this half is plexiglass, half is air, we have A over 2 as the dimensions of these plates, and D is the separation between these plates. Now we can write the capacitance of the plexiglass capacitor. Cp is equal to, because we have a dielectric, it's kappa times epsilon 0, the area of the plate, which is A times A over 2, divided by the separation between the plates. And for the air capacitor, we have epsilon 0, permittivity of free space. The area is A times A over 2 divided by the separation between the plates. Now, how do we calculate the equivalent capacitance when we have two capacitors in parallel? We simply add up the capacitances. The equivalent capacitance is Cp plus C0. So we have the same area, epsilon 0, kappa plus 1, A squared divided by 2D. Because this would give us A squared divided by 2D. This is kappa epsilon 0 times that, and this is epsilon 0 times that. So we have A squared over 2D times epsilon 0, kappa plus 1. Now this is the equivalent capacitance that we see. If we calculate this capacitance, let's do that. We have epsilon 0, which is 8.854 10 to minus 12, A squared, and then we have kappa plus 1, so we have 3.4 plus 1, A squared divided by 2D. So what was A? A was 12 centimeters, so 12 times 10 to minus 2 squared divided by 2D, 2 times 4.5 millimeters, 4.5, 10 to minus 3. So this gives us the equivalent capacitance as 62.3 picofarads. So it's 10 to minus 12. Now, if we move on to part B, we're asked to find how much is the energy stored in this capacitor. The energy stored, U, is equal to 1 over 2 equivalent capacitance times the potential squared. So this would be epsilon 0 kappa plus 1 A squared V squared divided by 4D. Because we had 2D in the capacitance, we have an additional factor of 1 over 2, so we have 4d at the bottom. Now we can evaluate this for the given numbers. We will see U is equal to 1 over 2. The equivalent capacitance is 62.3 10 to minus 12 farads squared, 10 to minus 12, and then we have the potential 18 volts, so 18 squared. So we obtain for the total energy stored, U is equal to 1.01 times 10 to minus 8 joules. And in part C, we now have a capacitance, a new capacitor. It's just an air capacitor. The capacitance is epsilon 0 A squared over D, because we have removed the plexiglass, remember. Now we're left with A squared for the area of the plates. And this will give us the new stored energy as 1 over 2 CV squared. So that's going to be 1 over 2 epsilon 0 A squared over D V squared. This is our new stored energy. Okay, now we see that the stored energy U on top was kappa plus 1 over 2 times this stored energy. So I observe that U is equal to kappa plus 1 over 2 times U prime. So if you take the ratio of these two, you will see we have kappa plus 1 over 2. So this tells us that U prime is equal to 2 over kappa plus 1 U, which is 2 over 4.4, because kappa was 3.4, 2 over 4.4 U, and we find that U prime is 4.59 times 10 to minus 9 joules. So the stored energy decreases for the same potential being applied. So it seems that there is an advantage to having this plexiglass in there. Okay, so we talked about a capacitor that is half plexiglass, half air. And to find the equivalent capacitance, we note that the two top and bottom plates are connected to the same potential, to the same battery. So Cp and C0, the capacitance of the plexiglass and plexiglass capacitor and air capacitor, they are parallel to each other and connected to the common battery with potential V. Epsilon 0 area over the separation is our parallel plate capacitor capacitance. For the plexiglass, epsilon 0 is replaced with kappa epsilon 0. And I note that because it's half filled with plexiglass, I have A over 2 and A as the dimensions. So these are square plates. So I see that the capacitance here is kappa epsilon 0 A squared over 2D, but for the air portion it is epsilon 0 A squared over 2D. For parallel capacitors, the capacitance adds up to epsilon 0 kappa plus 1 A squared over 2D. The energy stored is 1/2 C equivalent V squared, so that's what I substitute here. And if I remove the plexiglass, the new capacitance becomes epsilon 0 A squared over D, because the area of the air capacitor increases. And I note that in this case, the stored energy, which is 1/2 CV squared, is less than the initial stored energy by a factor 2 over 4.4.